All right, in this question, we're tasked with calculating Kp, so our equilibrium constant in terms of atmospheres or partial pressures for all of our gas-phase components. And we're given an initial amount. So this word here, a flask is charged. That just means that we're filling with 1.25 atmosphere of A. So I read that as the initial pressure of A. All right, so we're given an initial pressure, and as soon as I see that, I'm like, oh, okay, that's my I in the ice table. This is probably leading me down to setting up an ice table. The second piece of information we get is that the equilibrium concentration of A is 0.5 atmosphere. And the question is, what is the value of Kp for this reaction? So I look, if I want to calculate Kp, I need the partial pressure of A. Don't do that. That would be wrong. The partial pressure of B and the partial pressure of C divided by the partial pressure of A. All of these must be at equilibrium. All right, so I'm not going to be using the 1.25 because like that doesn't plug in here because that's not an equilibrium value. It's an initial value. I know this right off the bat. That's 0.50 atmospheres. That's given to me at equilibrium. Becca, the concentration, the pressure. Come on, my gal. At equilibrium, the pressure of A is 0.5 atmosphere. Technically, it's a proxy, but I should have written pressure. All right, so I know what that is. I need to find partial pressures of B and C to answer this question. Okay, so I could do this very quickly. It's not that challenging. What kind of flask is that? All right, here's my, can't do it, guys. Let me draw a nice round bottom flask. Okay, I fill this sucker. I've got 1.25 of A. All right, so time passes. Okay, time goes by. I let it reach equilibrium. At that point, I have 0.5 of A. So I lost 0.75 of A, which of course I can't lose mass. I must have made some A, B, and C. So consumed A, made B, and C. And I need to know how much of those two I made. All right. The math here is not super hard, but let's set it up formally as an ice table. So A goes to B plus C. Okay, they're all gases, so they're all included here. They all have a seat at the table. So initially, I have 1.25 atmospheres of A, and I have no B or C. Since the question doesn't say anything about adding B and C, we can make it pretty deep. We feel good about saying that that's 0 to start with, okay? Then there is a change, all right? The change represents this part, change, okay? That time, as it's approaching equilibrium, okay? And it gets there. And then at equilibrium, we know we have 0.5 of A. All right. So we can fill in the rest of this table by using the stoichiometry. Okay. Every time A reacted, so I lost some A, right? I know, and I already said what that was. 1.25 minus 0.75 gives me 0.5. Okay, so we'll wind up setting this up. This is an equation here. So 1.25 minus x equals 0.5. So what is x? Well, x is just 1.25 minus 0.5. Okay, that's 0.75. All right, so what happened to that 0.75? Well, every time an A was consumed, we made one B and one C, all right? Those coefficients, the stoichiometric coefficients are just 1. So the change for B and C as A was consumed was the plus X, and plus x. So my equilibrium is 0 plus x, which means it's just x for both of these. And I just solve for x. This is 0.75. This is also 0.75. Now I have this whole equilibrium row filled in. I know all of the equilibrium partial pressures. So I can go back up and calculate Kp now. Kp equals 0.75 times 0.75 divided by 0.5. That is 1.125. And that's right there. Okay, so this equals 125, which is rounded to 1.1. And that's our answer.